So today we're going to take a look at the 4680 cylindrical cell form factor and understand how, if we had the job of technically constructing such a form factor, what are some of the innovations we would need to do in order to get there. Before we can understand that, we also need to understand the limitations of the current form factors or the previous form factors, which are the 18650 and the 2170 cylindrical cells. With that understanding of the limitations, we can then solve those limitations and proceed to a larger form factor. So starting with the limitations, why was the 18650 or the 2170 form factor not good enough to get us into many years into the future of battery technology? Well, the reason boils down to a graph that Tesla showed in their Battery Day event in last year in September or October. And it looks something like this. So on the x-axis we have the cell size. And then there are two things to look at, right? The first is cost reduction. So cost reduction looks something like this. And the second thing to look at is the efficiency or vehicle range, right? So efficiency or vehicle range. Now, what we see with increasing cell size is that there is a cost benefit, right? So the cost reduces as you increase the cell size, and you can think of that, visualize that in a way that in 18650, which is somewhere here on the graph, that is a smaller unit, right? So your smallest unit that you're using to create a battery pack, that is somewhere over here, and that is on a smaller size. So each cell has less amount of energy. Now, if you have to pack multiple of these cells, there is some overhead, and this overhead is in terms of connections, wires, sensing, and getting once the electrons get to the casing of the cell, you have to carry them. You have to connect the cells in series, in parallel, carry those electrons, group them together through collector plates and all kinds of stuff to get them to the high voltage output of the battery pack. From there, it goes to the motor controller, the DC and all kinds of stuff, right? So if you have a smaller subunit, so if you have the 18650 subunit, or that's the smallest unit that you're working with, you have to connect many of these cells in series and parallel configurations to achieve the battery pack specifications. If you choose a 2170 form, or cylindrical form factor, then you have to use lesser of these cells than you had to in the 18650 format. And because you have to use lesser of these cells, what are some of the advantages and disadvantages of doing that? The advantages are that there's less overhead. So there's less number of connections, there's less number of wires, there's less number of plates that are needed to collect all the electrons. There's less number of sensing inputs that are needed on your battery management boards. So there is less overhead. So that is the advantage. The disadvantage here is that each cell of a 2170 format has more energy than an 18650 format. So the important thing is that if there is a cell failure, then that energy that is released by that cell has to be properly contained, right? So in a 2170 form factor, the energy that will be released by the cell if it goes into thermal runaway because of any types of problems that we saw. Some of the problems we saw in GM's Bolt fires were internal shorts caused by torn tabs, folded separators, those kinds of manufacturing defects. If they come into a 2170 form factor, they will lead to a lot more energy being released than an 18650 form factor. So that is a disadvantage that inherently comes with a larger form factor cell, something that a pack designer needs to think about, cater to, and properly assess when they're building their pack, when they're stacking these cells, is if one of these cells fails, then how do I make sure that that failure doesn't propagate to adjacent cells? And what I'm trying to say is that that job is a little bit easier in an 18650 format because it holds less energy compared to a 2170 format. So those are some of the advantages and disadvantages of moving to a larger form factor. But what we found, or what the industry found, is that moving to a larger form factor still has its perks and still the way to go, right? So if an 18650 falls somewhere here in the graph and then 2170 falls somewhere here, we see that by going to a 2170, we can get a increase in the vehicle range or the efficiency, right? And we can also get a larger cost reduction in a 2170 form factor. So more cost reduction and a higher vehicle range, so we're looking good. As long as we can take care of the higher energy density contained inside our smallest subunit, which is a larger cell. Now, if we move to a 4680 format, 4680 falls somewhere in this sweet spot, right? You see this sweet spot here? After this spot, the vehicle range starts to reduce. So this is the sweet spot that was dictated in the Tesla Battery Day event, which is where they wanted to position themselves, the 4680 format, which is the cell diameter being 46 millimeters and the length being 80 millimeters. In this sweet spot, they were able to get a higher range than the 2170 format and a larger cost reduction than the 2170 format. But there are technical limitations that were preventing the industry in moving forward more than the 2170 format for the past couple of years. These technical challenges had to be overcome in order for us to get to the 4680 format. So let's now understand what some of these technical challenges were and how they were overcome. Okay, so we have an 18650 cell, which has an 18 millimeter diameter, 65 millimeters in length. Then we have a 2170 cell, which is 21 millimeters in diameter and 70 millimeters in length. And then we have a 46 millimeters in diameter and 80 millimeters in length. Okay, so we have increasing diameters and increasing lengths. Now, what allowed us to go from here to here, but until now, or until recently, didn't allow us to go from here to here? One of those things was cell resistance, or the heat that is generated in the core of the cell. To understand this, we need to take one step back. Okay, so inside a cylindrical cell, if you've taken one of our courses, you know that inside, if I break the cross section of the cell, what I'll find is anode, separator, cathode, and the electrolyte. And if I look at the anode, there will be the current collector, the binding membrane, and then the active material on top of it. And the way that these are structured are in the form of a jelly roll. So if I break the cross section here, what I'll find is a cylindrical jelly roll inside it. which is housing the anode, the separator, the cathode, and then the electrolyte. Now, if I look at this jelly roll, and at each point of this cylindrical jelly roll, I have active material, and this is where the lithium ions are housing themselves, doing the intercalation reaction or intercalation mechanism that allows them to interchangeably go from the anode to the cathode and vice versa, based on if the cell is charging or discharging. Now, if I look at the very core of the cell, every time the lithium ions are going from the anode to the cathode, there's electrons that are also flowing, right? And these electrons need to flow they need to come out of the cell and produce work, right? The way that the cell is structured, the current collectors, in this case, are connected using cell tabs. This is again something that we've learned in the courses, that in the current collectors are connected to cell tabs, which are these metal plates that are connecting the internal of the cell to the cell casing. So the negative here and then the positive here, you have cell tabs, metal plates that are connecting the current collectors to the cell casing. Now, if you look at the very core of the cell, from here, there are electrons that need to, right? There are electrons that need to get to the positive terminal to be able to exit the cell. Or they need to enter the negative terminal and reach the core of the cell. And this pathway, if you imagine this pathway for a conventional lithium-ion cell, the way that the tabs are placed is if I unroll the jelly roll, what I'll find is, say this is my first membrane, which is the anode, then I have my separating membrane on top, right? And then I finally have my cathode membrane. So I have the anode, then the separator and the cathode. The tabs, if I unroll the full cell, the tab for the cathode will be somewhere here, right in the middle. Similarly, the anode. And this is what is connecting the whole current collector, the whole roll. There is this one pathway for electrons to exit. So the electrons that are over here, or if I unroll on the other side as well, right, these have to travel the largest path to exit and to enter the cell's terminals. And electrons traveling a larger path and going through this little bottleneck all amounts to larger cell internal resistance. If we have larger cell internal resistance, that means when the cell is functioning, when the cell is charging, when the cell is discharging, there will be more heat that is generated inside the cell, inside the core of the cell. And the heat that is generated at the exterior of the jelly roll might have an easier path to get to the exterior of the cell casing and then transmit to the surroundings where there is cooling plates, all kinds of stuff to keep the cell casing cool. The heat that is generated on the exterior part of the current collectors has an easier way out, right? But the heat that is generated in the core of the cell has to travel through many, many layers of current collectors, of the electrodes, the separating membrane, to reach the exterior of the cell where we have coolant flowing and keeping the cell casing cool. So what was happening is when we had the core of an 18650 format cell, these electrons had to travel a smaller distance to reach the exterior or the cell cell tabs, which led to the cell casing. So the path for this electron to reach the cell tab and then the cell casing in an 18650 was smaller than a 2170, because of which there was lower cell resistance. Lower cell resistance in an 18650 cell as compared to a 2170 cell, which means that the heat that was generated in a 18650 cell was less than what was generated in a 2170 cell. Which also means that because the heat generated inside a 2170 cell is more, it also has to travel a larger path to reach the exterior casing, which is being kept cool by the coolant flow of the battery pack. Now there was a limitation here, right? After a point, if I keep increasing the diameter, if I go to a larger diameter than the 21 millimeter diameter, the heat that was generated inside the core, the very core of the cell, was taking too long to get through all the layers of the jelly roll and reach the exterior casing. And because it was taking too long, the interior of the cell, the core of the cell, was increasing too much in temperature. And because the temperature of the core of the cell was increasing too much, it meant that I can't take as much current or cannot put as much current into the cell in a short period of time. If you give me unlimited amount of time, maybe a 2170 form factor would still be okay, right? Because the heat that is in the core of the cell has unlimited amount of time to travel to the exterior of the cell. But if I'm taking a lot of current and a lot of performance from the cell in a short amount of time, that means that the heat that is being generated in the core of the cell has to quickly reach the exterior of the cell from where the coolant does its job. And in the high-performing applications that we need today, this has to happen. We need to draw high amounts of current to have high-performing cells, and because of which we have high-performing vehicles, we have longer range vehicles, we have vehicles that will be able to accelerate faster, and all kinds of stuff that we expect from the end product. But in order to achieve that end product specification, we need to have a mechanism through which heat can travel from the interior of the cell to the exterior of the cell in a much more efficient way. Okay, so if we take a look at the four main things inside the cell, we have the anode, the cathode, the separator, and the electrolyte. Right? These are the four main things inside the cell. In some cases, you'll have more than one separator, but these are the four main elements when you unwrap or unroll a cylindrical lithium-ion cell. Now, we looked at that the issue for going from a 2170 format to a 4680 or larger format was that there was a lot of heat that was getting trapped in the core of the cell. And this was because when we unroll the jelly roll of the cell tab is found somewhere in the middle, right? And this is the pathway for electrons to flow from here, from here, from here, and if I unroll from all the way on the other side as well, right? So if I unroll this fully, and I have a cell tab here, then from here, everywhere inside the current collector, there is a single pathway for electrons to exit and enter. So this electron has to travel a large distance to exit the path, the tab, to reach the cell casing, and then maybe connect it to other cells, perform usable work inside an electric car. This electron is going to be going to your motor, it's going to be going to your dashboard electronics, it's going to be operating all kinds of stuff, right? But it has to start its journey here. And this journey is long as compared to this electron. So Because of the unevenness and because of this bottleneck here, we have higher resistance of the cell, higher internal resistance of the cell, more heat generated inside the cell, and a limiting factor that is stopping us from increasing the dimension of the cell. So the first thing that pops up in your mind is, okay, if this is the limiting factor, let's put multiple of these cell tabs, right? If I put one here, if I put one here, if I put one here, and here, and here, and here, then this electron can take the shortest path out. Similarly, take the shortest path in. This electron can take the shortest path out, shortest path in. This electron can go from here, come back in from here. This electron can go from here or can go from here, whatever the shortest path is. So what we've just done is, instead of one tab, now we've put many tabs. And this is an improvement over the previous design. But there's still one problem. There's a problem that you have a current collector plate, which is a nice big solid roll of copper, aluminum, or another type of metal that will allow a low resistance path for electrons to be collected and flow out of the cell's terminals. Now this nice big conduction layer has these tabs, which are these metal metal plates or metal little metal connectors that are joined to this current collector over here. They're joined in order for providing that pathway to the exterior of the cell, right? And these joints, as we saw in the GM Bolt battery failures, these joints are susceptible to vibration failures, they're susceptible to manufacturing problems, and it's just not a good solution. Any type of joint still offers, if you look at a joint over here, right, then you have, it'll look like a metal is connected to another metal, but if you look at a microscopic level, you have some small pathways for electrons to flow. It is not a nice continuous path for electrons to flow, a nice low resistance path for electrons to flow. So how did Tesla solve this with their tabless electrode? So I hope this video helped you understand the limitations of the industry that are stopping it from, or were stopping it from, going from the 2170 form factor to higher cell dimensions, and why the industry moved from 18650 to a 2170 cylindrical form factor in the first place. Now, to learn more about the A to Z, about cell technology, about battery pack design, about BMS technology, and about how the leading experts like Tesla solved the problem through deep core innovations like tabless electrodes, right? Like 4680, the 4680 cell, one of the things that enabled the 4680 form factor was the tabless electrode patent that Tesla put out, right? Understanding how the cell construction is changing. And these are very subtle things when you read about it in detail, when you learn about it in detail. And once you know them intuitively, you're like, wow, how come I didn't think about this before? But if you have to be on the cutting edge, if you have to be innovating, you have to be looking at these things from first principles and not just accepting what has been put your way. In this case, Tesla didn't accept that the 2170 was the best we could do in terms of cell design, in terms of cell form factor. They wanted to strive for higher efficiency. So how did they go from this problem of heat generating inside the core of the cell and the bottleneck of the cell tab? How did they go from there to a tabless design? How did they then enable the 4680 form factor? These are some of the things that we're going to be looking at in the Battery Masterclass 2.0. So I encourage you to check that out. We're also going to be taking a look at the newer solid state technologies that Toyota is putting huge amounts of funding into. So these are the cutting edge, these are the things that will define the future of battery technology. So now is the time. Now is the time to understand these things in clarity, with clarity and with detail, so that they form and you're able to form an intuitive understanding of these concepts, where we are in the battery technology space till today, so that you are able to then take a look at these new inventions and be like, wow, like this is amazing, right? And to get to this point, to be able to read, for example, a patent of this new cell designs, to be able to call out like this cell innovation or this battery pack design is not going to work out. It's really like, I don't know what the hell they're talking about. It's not going to work out because of this, and this. Versus, this is great. This is going to really strive and push the boundaries of battery technology, of cell design. How do you make that distinction? How do you offer that distinction to be able to clearly identify a failure versus a breakthrough to maybe your employer, or maybe to incorporate this in your own business, right? So in order to get there, we've put out a detailed curriculum which will take you through cell design, which will take you through battery technology, will take you through BMS design, and allow you to intuitively learn these things through a hardware kit, right? This hardware kit is shipped to you worldwide and allows you to practice battery management algorithms. It allows you to practice and actually work with a real lithium-ion cell, be able to charge it, discharge it, and see how the battery management system, the algorithms that you write, how are they performing in real time, right? So the learning can't get better than that. The intuition is built through these exercises, built through these experiences. And so that's why I encourage you to check them out. That's why I encourage you to jump on this opportunity that's not going to come again and again. This is a cutting edge space that is moving fast. So I encourage you to, if you've not already caught up, let's catch up to the industry today. And then from there, let's innovate and be on the cutting edge and the cusp of battery technology. Look forward to seeing you in the courses. Thanks so much for taking the time to check out this video. And if there are any questions, I'd be happy to help. Just hit reply to my email. And if you don't have my email address, it's akshay@makermax.ca. That's AKSHAY at Makermax, MAKERMAX.ca. Just shoot me an email anytime with your questions, and I look forward to seeing you in more of our courses.